Even though Neptune is 30 times further from the Sun than Earth, cold and dimly lit, it's still thousands of times closer to us than the nearest stars. And yet, it may turn out to be a great place to live, and a gateway to those stars. So today we return to the Outward Bound series to look at how we go about colonizing icy giants like Neptune. We've looked at colonizing gas giants before, but mostly in the context of colonizing their moons, and not so much the planets. Ice giants like Neptune and Uranus are very common in the universe, as best as we can tell, and aren't actually that much more massive than Earth, generally only being 10 to 20 times as massive. Not like the bigger Jovians, which are many hundreds or even thousands of times larger. Indeed, their surface gravity, for a given value of surface, is pretty close to Earth's own. Uranus has 89% of the gravity Earth does, and Neptune has 114% of Earth's gravity. Only Venus is closer, at 90%, and it is in some ways harder to colonize than either of these two planets. Akin to the Venusian sky cities, we could possibly build cities which float in Neptune's atmosphere. This, however, would be much more challenging to pull off because the winds on Neptune are murderous. Even on the planet Uranus, which has lower wind speeds in certain spots due presumably to this planet being tilted on its side, high wind speeds would still be a big problem. They are also potentially a source of massive power though. Wind is tricky on Earth due to speeds ranging from useless to hurricane force. You wouldn't use a classic windmill on places like Neptune though, you'd use something closer to a jet turbine. Power is a pretty big issue for these outer planets because sunlight just isn't strong enough so far from the sun to be a viable way to power an entire colony. These planets aren't dark though, they get lighting on par with what you'd expect in a room lit by normal light bulbs. We have some alternatives though. We could also beam power out as we discussed in the Power Satellites episode a couple months back. As already mentioned, we can tap the atmosphere for wind power, as well as the nuclear option. But what we really want is fusion, especially for these two planets as they have large stockpiles of helium-3, the preferred fusion fuel for aneutronic fusion. We will discuss why aneutronic fusion is seen as better than normal fusion in a moment. I mentioned the other power sources just to make it clear we have alternatives even if we never achieve portable fusion, but Uranus and Neptune in particular are both places we'd most likely hold off fully colonizing until we either did have it or knew it wasn't in the cards. So let's follow an intrepid traveler on a journey to colonize Neptune. It is the year 2400, and while Uranus has some basic stations on its moons already, Neptune only has a few small scientific outposts in its atmosphere, and on its largest of 14 moons, Triton, the coldest object in our solar system. We are colonists leaving from Earth on board a colonization fleet that's the first to feature fully functional aneutronic fusion devices. And as those rely on helium-3 for fuel, establishing some big helium-3 refineries in the outer solar system is high on everybody's list. We've had fusion technology for a while, but they are big and clunky power plants, and while those improved, they never got too good at powering ships. The problem with typical neutronic fusion, like that using deuterium and tritium, is that most of the energy from that fusion event is in neutrons, and these are hard to tap for energy and do a lot of damage to whatever containment system you are using. Aneutronic fusion is exactly that, fusion that doesn't produce many neutrons, but instead mostly stable and charged particles, which should be easy to get electricity from. Aneutronic fusion is far harder to do, but represents probably the best path to relatively compact and lightweight fusion reactors, like the kind we'd like to use in spaceships or small colonies, places where mass and size matter a lot, and probably maintenance too. Someone went through the difficulties in inventing one, which opened the gates for us to the outer solar system, not just Uranus and Neptune, but all of the Kuiper belt, which is vastly larger and more massive than the asteroid belt. And indeed it even opens the gates to the Oort cloud and other solar systems beyond. We now have a ship engine able to produce a significant thrust for days or even weeks at a time. Our Neptune colonizing fleet will burn out toward Neptune at 0.2 G for half the trip, then flip over and burn down, arriving 5 weeks after our departure from Earth, and reaching a maximum velocity of 1% light speed. Like in The Expanse, we can use constant acceleration in place of rotating sections to provide gravity, though in this case, just a little better than moon gravity, but for a 5-week trip, that's fine. Now, as we've noted before, this constant acceleration approach is not usually a good one since it's very fuel wasteful. By preference, you'd accelerate faster, but not for as long, cruise, then flip over and burn down to stop. However, in this case it is okay because fuel and propellant don't matter too much, because that's the hypothetical maximum acceleration out of this style of fusion drive, 0.2 G, and that's probably being optimistic. So we just burn the whole time because it's not that long a trip, and indeed we are quite capable of handling a much higher acceleration, as we are not exactly human. The fuel is fairly rare, but the propellant, hydrogen in this case, is very common, so we can blow it like it was going out of fashion. If we could accelerate faster we would, and we'll talk about how we might later, but fusion drives and high thrust don't work well, at least not if you want a high final speed. We'd like to be able to do a full G like we were standing on Earth, and in truth we'd like to do more and we could handle a much higher acceleration. This is the 25th century after all, and we've been picked to command this fleet because we are an experienced traveler and colonist. Few people in the solar system have been to as many of humanity's new worlds as we have, and we've made a career of colonizing planets over the centuries, and we've become more than a bit of a cyborg in that time. Long gone are the days of roughing it or making small outposts to slowly grow. Our fleet is carrying state-of-the-art, expandable rotating habitats with it, huge amounts of colonial gear, and most of those ships will be immediately departing to either pick up tens of thousands of more colonists from Earth or race off to the massive factories of the Belt, Triton, and the Jovian moons to pick up more equipment. We will need it too, because while we'll be temporarily housing people in those rotating habitats in orbit of Neptune, we are going to be building massive refining facilities right inside of Neptune's atmosphere. Indeed, it is going to be the single largest construct humanity has ever created. It will even outstrip the orbital rings of Earth. After all, those refining facilities are going to be similar to those rings, but Neptune is a lot bigger than Earth. See, there's lots of ways to mine gas from a gas giant. You can dive down and scoop it up, for instance. But we are going to do this with the biggest bucket wheel excavator in the galaxy, namely a giant ellipsoid orbital ring which, incidentally, looks like a chainsaw. A chainsaw fit for a god like the one the planet is named after, Neptune's chainsaw. This is the 25th century. We don't do space colonization small or on shoestring budgets anymore. Billions of people live and work in space, and factories the size of small moons convert megatons of ore into products every day. Ships that dwarf the biggest oil supertanker crawl across the solar system delivering goods, and soon they will sprint, not crawl, as superior engines permit them to race across the void, fueled by the near-endless stockpiles of helium-3 on Neptune and the other gas giants. For now, many of those ships are carrying out segments of Neptune's chainsaw for assembly, and many of our passengers are not colonists at all, but folks traveling to view the historic event, the colonization of the last planet in the solar system. Truth be told, we find their presence rather irritating, standing around gawking and getting in the way, but this mission requires a lot of resources and backing, and spectators were part of the cost for that. One of them, on the younger side, asks us why it is such a historic event. We explain, until now, humanity has been essentially limited to using either stuff like uranium or thorium for fast ships, or dependent on powerful energy beams from huge collectors near the sun. Those work, and energy beaming from the sun is actually quite efficient, and part of this expedition will be making that system even more useful, but ultimately we were dependent on those. We couldn't make massive amounts of power locally and in a compact way. In a generation or two, a small colony will be able to buy its own aneutronic reactor, cheaply fill a tank with helium-3 and deuterium, and have a reliable local power source. With fusion and some decent local manufacturing ability, they can set up anywhere they want, even way out in the Oort cloud, and only need infrequent refueling. Nobody can threaten to jack up their power beaming rates or cut them off. A single tanker of what Neptune will soon produce will let a colony last centuries or even millennia without needing any new fuel. But why is the chainsaw going to be shaped funny, elliptical, not circular like Earth's orbital rings? Our passenger asks. Orbits come in many forms, including some rather peculiar ones. Almost every natural orbit is an elliptical one. If you can make a stable orbit, you can make an orbital ring that matches that orbit. You can even make some that wouldn't normally be possible. Our goal for the Neptunian chainsaw is to have an elliptical one that drops down into the atmosphere on its low portion and rises high up afterward. We will scoop gases up in big buckets which will enter the ring's transport system and be shoved along, refined as it goes for what we want, and raced up to fill tanker ships. Now we have options like this for Earth too. You could put two big circular rings around Earth connected by a third elliptical one. Indeed, that would keep the low portion of the ring just over the atmosphere and lower tethers down to suck up air. But what's interesting about Neptune is that its gravity is higher than Earth's, if not by a lot, and on the upper portion of that ring, it will be a bit lower. We can build domes on those sections with normal gravity, and still get protection from micrometeors and radiation by the thinner atmosphere up there. Meteor protection matters too, since all of the gas giants have rings of debris around them, even though they're not as big as Saturn's, and thus have lots of meteors. While there's not enough light there to grow most natural plants, it is enough to comfortably see by, though Neptune's day is only 16 hours long, so you'd want supplemental lighting. Fortunately, there is an effective near-infinite power supply right below, and Triton is almost as large as our moon and can provide plenty of construction and manufacturing materials after we've consumed its tiny siblings. Triton is the last and smallest of the large moons in our solar system, and actually has more mass than all the other Neptunian moons smaller than itself combined. If you head down deeper into Neptune's atmosphere, it's got interesting layers of clouds. Clouds on Earth are made of water, but clouds on some other planets can be made of methane, ammonia, or sulfuric acid instead. Neptune, though, is thought to have many different layers of clouds made of different things as you go down. Neptune and Uranus, which are small gas giants but which you can also think of as ice giants, have a lot more volatiles proportionally than Jupiter has, for instance. Volatiles, things like nitrogen, water, carbon dioxide, ammonia, methane, and sulfur dioxide, are always of interest to us, and if we're willing to dive deeper down, we can find clouds of them for harvesting. We often think of mining space for metals, precious ones like gold or ones for construction, but these chemicals we need as the basic building blocks for life itself are very precious. Triton is also a good source for volatiles, and its surface is covered with these ices. But since demand is growing, and since mining that ice is more difficult than just scooping or pumping it up, it would still be advantageous, and indeed preferable, to mine such volatiles from Neptune's atmosphere. Now we have a few ways to get down to those deeper levels. The first, of course, is to suspend yourself from a tether, hanging from Neptune's chainsaw, the orbital ring system that encircles Neptune we discussed earlier. The second would be to fly down in some interesting mixture of plane and submarine. The third would be from a balloon or even a giant turbine. A problem with using balloons on gas giants, as opposed to Venus, is that they are mostly hydrogen with a bit of helium, our two preferred lifting gases. You can't use something as a lifting gas inside an atmosphere composed of that. On Venus, we can even use oxygen as one because the atmosphere is made of denser gases, but Neptune is almost 20% helium, so we could use pure hydrogen, likely in plentiful supply, as you refine out the helium and helium-3. And you can heat it too, since we've got access to power, or you can just run a giant engine and coast along with the terrifying winds. But you could also keep yourself pressurized like a submarine and drop deeper instead, to where you'd be buoyant. Hanging down from the tethers seems rather neat though, and since the sun isn't really your source of light, there's no need to build flat. You don't have to make your orbital ring wider to support more domes, though you can. Instead, you just build up or down from it or another supported platform. Hanging down is as structurally sound as building up like a skyscraper. The only difference is that one relies on tensile strength, whereas the other relies on compressive strength. So you could have hanging cities, lighting themselves, suspended over Neptune and down into the atmosphere, glowing in dim, dusky light, hanging down like immense chandeliers. Chandelier Cities. A book series I'm fond of, Gregory Benford's Galactic Central Saga, references chandelier civilizations at one point, but I never got a description of them. I've always wondered if this is what he had in mind. I should ask him one day, but regardless, we shall call these chandelier cities, and they're ideal for ice giants. I imagine they'd be absolutely stunning to approach by plane, hanging there among the clouds and storms. But the atmosphere, while it gets much denser as we go deeper, is not the majority of Neptune. Indeed, it has a very large mantle, which is perhaps a dozen times more massive than the entire Earth, and which is composed mostly of the ices that make us call it an ice giant. With all that water, ammonia, and methane ice, it is massively rich in the building blocks we need for artificial ecosystems. Getting down there to mine it would be tricky, but active support, like our orbital rings, can be used to make stuff much stronger against crushing too. However, it's quite likely it rains diamonds down there, and we could get quite deep just relying on strong materials. Because of this, we'd be able to harvest a lot of that diamond and possibly other materials, or even get to live in diamond-hard domes deep down in Neptune. I should note, though we always hope the future will be peaceful, that these sort of buried colonies, hidden and shielded by huge atmospheres, are good places to live during conflicts. For that same reason, you could see a lot of rotating habitats bury themselves deep under ice or rock in asteroids and comets, or import a lot of hydrogen and helium not just as a long-term fuel supply, but additional shielding. They can wrap their habitat in cheap tanks of gases. It's hard to drill deep into the Earth, not just because of the pressure, but the rising temperature, but it's not as bad inside Neptune's mantle as it is in Earth's. Eventually, there is a core, which is essentially a rocky planet all of its own down there, but you'd probably have to remove that atmosphere to get to it. We'll talk more about mining planetary mantles and cores in our Earth 2.0 series, which will start next month. For ice giants in other solar systems, ones nearer the Sun, as some might well be, you might blow that atmosphere off and use it like a rocket flame to push the planet into the Sun's habitable zone, and be left with a rocky planet when you're done, which is ready for terraforming. For this, we could employ the fusion candle we discussed in Colonizing Jupiter. We are not expecting to do that with Neptune though. The long-term plan is just to build more Neptunian chainsaws and regular circular but wider orbital rings around it, till we encompass the whole planet. This is something we call a shell world, and we discussed it in more detail in the Mega-Earths episode. Even for advanced civilizations living in the 25th century, building a shell world around Neptune would take a really long time, but it can be done incrementally, just adding more rings and chandelier cities till you encompass the whole planet. Then add dirt and water and lighting, potentially sun moons orbiting once a day, vast fusion satellites producing light. We have a power supply for that and such an enormous construction project, and as we mine Neptune's atmosphere and mantle, we can slowly contract those rings and therefore contract the shell world too, keeping it to a size that provides normal Earth gravity. Incidentally, even if you eventually expanded your orbital rings to make a complete shell world, you could keep those chandelier cities we mentioned earlier hanging down under the shell. They might also work very well on planets or moons with icy shells over deep oceans, like Europa. Neptune's own moon Triton might have a subsurface ocean too. There is a lot of gas on Neptune, and it raises the question, what would we do with it all? For that matter, with Uranus being closer, and maybe easier to mine with its lower winds, who is buying our helium-3? Well, first, the helium-3 concentration on Neptune is 19 parts per million, which is a little higher than Uranus's 15 parts per million helium-3 concentration. But second, in a fusion economy, that extra distance to Neptune from the inner solar system, as opposed to Uranus, is actually fairly irrelevant. Indeed, parts of the asteroid belt will sometimes be as close to Neptune as Uranus, and this difference in distance doesn't much matter anyway. It's a minor amount of delta V compared to the energy that fuel contains. Tankers carrying helium-3 and deuterium would still move slow. It won't spoil and has a high energy density, so there is no reason to move it quickly and waste energy or capital on very large engines. Moreover though, we'll be seeing a lot more people moving to the outer solar system now, particularly the Kuiper Belt, where land is cheaper and plentiful, but they'd have to bring their own sunlight. And as rarely as one would need to bring in fusion fuel, folks can wait a couple centuries till Neptune is closer to them again on its own long orbit to refuel themselves. But when asked, our traveler, admiral of this colonial fleet and figurehead governor of Neptune, says that it's really all about ships, and not just ones with aneutronic fusion drives. See, you can bounce a laser off a sail and make it go further away, or even off to a side, by tilting the sail to bounce the light at an angle, but you can't move just sideways or inward toward the sun, not by bouncing alone. What you can do though is bounce a beam off something further out, and bounce it back in at your light sail, pushing you back inward toward the sun. The problem is, if you stick a mirror further out than your ship, you will push it away eventually. So it helps to have that mirror on something that is massive enough for the recoil to be negligibly small. Ice giants and their moons are perfect for this, as are larger icy bodies in the Kuiper Belt. They can also emit their own beams rather than bounce if they have a power source. Had nobody invented good, cheap aneutronic fusion, we could have gone about colonizing the outer solar system this way, beaming energy out from massive solar collectors near the sun and using those, bounced back, to push ships inward, and to power these cold, lonely pushing stations. Even with fusion though, it's still a nice path, because it means ships need not rely entirely on onboard fuel and propellant. Indeed, the combination of the two will allow even better and safer and cheaper interplanetary travel. We said that this sort of fusion drive really only permitted a maximum acceleration of 0.2 g, and there are ways that could perhaps be boosted, but it could pull that while getting beamed energy, or even beam propellant, out to the ship. So you get laser highways inside a solar system folks could use to supplement their engine, but they could still operate without them too. It would be like jumping in the fast lane, and gives the benefits of both systems while removing many of the limitations of and dependence on each. Our traveler turned admiral turned governor though has even bigger plans than Chandelier cities, planetary chainsaws, shell worlds, and giant mirrors. Indeed, even plans beyond colonizing the Kuiper Belt and Oort cloud. Our governor plans to colonize the stars themselves. He tells our young tourists that one day the moons of Neptune will be giant shipyards, turning out colonial fleets to head out to the stars themselves. Armadas that will be built here and launch, not out to the stars, but in toward the sun, pushed by beams toward it and then sail past, pushed even faster by stellasers near the sun, running up to decent fractions of light speed, then back out again, ever faster, pushed on till they reach the Kuiper Belt, and then pushed even more from relays and lasers out there. Then they will cruise along ahead, massive interstellar arcs lit and warmed by fusion reactors, sailing off to yet more distant homes. Neptune, we tell our young passenger, will be the gateway to the deep ocean of outer space, the last big port of call, and it may be big indeed, with vastly more size and resources than Earth, with a near endless source of power, with all those moons and its own rings and Kuiper Belt nearby. It could become a massive kingdom fit for its namesake. If our young passenger returns to Neptune when they're an adult, they'll see a growing empire that they can reach in just a couple weeks' travel, and quite cheaply. It's an empire the governor himself will never lead. Once it's built up enough to build its own fleets for interstellar travel, he means to be on one of those, and tells our young passenger he hopes they'll join one themselves one day. The solar system is now a much bigger place, opened up far past the asteroid belt for settlement, but it's just a tiny corner of a vast galaxy. While not the last frontier of our solar system, Neptune is the last truly big one, and it's fitting it should serve as the gateway to the stars. So this is not the end of the Outward Bound series. We still have a lot of solar system to explore, not to mention other systems, and some places closer to home to revisit like the Moon or Mars. However, while we will continue our look at the ships that will get us to those other star systems, we're going to take some time to talk about colonizing a bit closer to home than even our moon. In the upcoming Earth 2.0 series, we'll be looking at colonizing our oceans and frigid poles and deserts and mountains and how we can use the technology we've discussed in this series to do it. We talked a lot about orbital rings today and structures hanging down from them, our chandelier cities. A lot of times we suggest structures folks aren't used to and can seem less safe as a result, even though they are often more structurally sound than things we use all the time. Ultimately, they use the same structural mechanics as a suspension bridge, so do the rotating habitats we often discuss. Most folks are comfortable with those because they are familiar, but if you're curious about the mechanics involved, so you can understand why a city hanging down from an orbital ring is as safe or even safer than a skyscraper or your house, I suggest trying out Brilliant's course, Infrastructure. As part of their Physics of the Everyday courses, Infrastructure has some great quizzes on bridges and skyscrapers, and like all their quizzes, they are meant to keep teaching, not just evaluate knowledge. The future is going to be a place of vast, awe-inspiring structures that dwarf anything we have now, and if you want to understand them and the challenges to building them, the Infrastructure course is a great way to do that. If you're interested in learning more math and science, and doing so at your own pace, you can go to brilliant.org/IsaacArthur and sign up for free. And also, the first 200 people that go to that link will get 20% off the annual premium subscription. So as mentioned, we'll be talking about colonizing Earth soon, and we'll start that off with a look at seasteading and making artificial islands in 2 weeks, then moving on to colonizing oceans after that. First though, we'll be exploring the human mind and talking about mind control and brainwashing, and our book of the month, George Orwell's dystopian classic, 1984. Make sure to subscribe to the channel for alerts when those episodes come out, and since this episode happens to be coming out on my birthday, I will shamelessly guilt everyone with that before asking you to please like this video and share it with others. It also happens to be the 4th anniversary of the channel and its original pilot episode. If you want to help support the channel on Patreon, you can find a link to that in the episode description below, along with our Facebook and Reddit groups, if you want to discuss this topic more. And should you visit those, I'd be curious what other places you'd like this series to visit when we return to it. Until next time, thanks for watching and have a great week.